Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be solving a really cool equation with complex numbers. 1 plus I to the power z equals z squared, and we're gonna try to solve for z. Now 5 days ago I had made a problem that looks like this, and this is actually very similar to the problem we're going to do today, with the exception of n being a positive integer. And of course, solving for n was fairly easy, relatively easy, because we were looking for positive integer solutions. Go ahead and check out that video. I'll try to share a link down below as well, and here too, so you can check it out and let me know what you think. So where does this problem come from? Where is the inspiration coming from, right? Well, I'd like to thank you, Physic Trapella, for this idea. Let's go ahead and see how we can solve this type of problem. Great, now we have 1 plus I to the power z equals z squared. Now, we have a complex base, a complex exponent, and it's the same thing as the complex number squared. How is that possible, right? It's really interesting. I think this is a great idea, by the way. If you have problem suggestions like these, please keep them coming, because I really love your ideas. Now, let's go ahead and see how we can solve it. Now, we're going to do some interesting stuff, and then we'll use a special type of function. Let's not name it right now, okay? So, first of all, I want to bring these on the same side. Obviously, I'd like to have everything on the same side, but before that, let's go ahead and do this. Let's square root both sides. What that does is eliminate the square and gives us something like z equals 1 plus I to the power z over 2. Now, here you need to be careful. Obviously, the square root of z squared is not just z. It could also be a negative z. But I'm just going to go with the positive solution, and hopefully you can deal with the negative solution on your own. Now, from here, we're going to try to bring these together. So let's go ahead and multiply both sides by the reciprocal of this expression right here, which is 1 plus I to the power negative z over 2. And of course, that's going to make a 1 on the right-hand side, right? If you multiply two reciprocals, you get 1 because the power will be 0. Now, we got everything on the same side except for 1, which is good. We have all the variables, all the z's on the same side. Now, what are we going to do next? So we're going to try to come up with something that looks like this, t e to the t. And the reason behind that is very simple. Lambert, thanks to Lambert, he came up with a function, and it's called w. And w basically takes an input like t e to the t, and that gives us t. So if you ask me what this function is, I would say it's the inverse of t e to the t. There's no expression that we can write Lambert for. That's why we have to express it this way with a w, okay? And sometimes people think that, oh, because you can't really express it like explicitly, that it doesn't exist. That's not true, okay? It's false. So now, how do we go from this to this? That's what we're going to do next, okay? Let's go ahead and see. Now, first of all, I noticed that I have a negative z over 2 and z here. But most importantly, you do need an e as the base. And here, e is not the base. That's not good. We don't want that. So let's go ahead and actually do this. If I have a number like a complex number like u to the power v, I can write it as e to the power v ln u. U and v are complex numbers, and this is called complex logarithms, okay? Now, how does that work with our expression? We can turn 1 plus I to the power negative z over t, negative z over 2. I don't know why I keep saying t. I made a differential system of differential equations on my other channel, Cybermath, and it had a lot of t's in it. Maybe that's why. So go ahead and check it out if you haven't checked it yet. And that published on Monday, which was yesterday, right? Of course, now, this can be written as e to the power negative z over 2 multiplied by ln 1 plus I. Now, the million-dollar question is, what is the ln of 1 plus I? That brings us to complex logarithms, right? How do you log a complex number? Well, there's an easy way to do it. If you consider the main, like the principal branch, you can basically just natural log a complex number like z, and it's going to be equivalent to ln absolute value of z, which you can also call r, by the way, plus I times theta. Usually we write z as r times e to the I theta in polar form, thanks to Euler, and then ln z would be ln r plus I theta. Of course, we're considering the principal branch here, so there are infinitely many solutions, obviously, right? So this is very compact. This is a really nice way of writing it. And you got to remember that this is a complex logarithm. This is a real valued logarithm. So they're kind of different. That's why some people will write log z, L-O-G, for the complex logarithm, because it's a logarithm, okay? Fine. But I just write ln. I don't care. Now, so what do we do then? We can basically find the ln of 1 plus I, just using this, right? What's the absolute value of 1 plus I? It's root 2, so it's going to be ln root 2 plus I times. Now, this kind of is like plotting this in the coordinate system, and that's going to give you pi over 4 as your principal argument. So this is going to be I times pi over 4. So basically, and you can write this as 1/2 of ln 2 if you want, if you're really super duper picky about it. But as you can see here, ln of a complex number is just another complex number in the form of a plus bi. And what's the name of this channel? A plus bi, right? Easy to remember, hopefully. Now, we got ln 1 plus I. We got everything we need, didn't we? Let's go ahead and put it all together. So now we had, last time, we had this one. So let's go ahead and start with that. Z times 1 plus I to the power negative z over 2, which I wrote as e to the power negative z over 2 multiplied by ln 1 plus I, which is this 1/2 ln 2 plus I pi over 2. Now, by the way, you could leave it like ln 1 plus I if you wanted, and just work with that. That's perfectly fine. But I don't like that. That's why I'm going to turn it into this. So it's more clear. Now we know what the log of a complex number is, hopefully, right? Now, you can definitely distribute this, but don't do it. It's not going to do you any good. But oops, I forgot to write the right-hand side is 1. Now, what was our goal again? Let's just remember. We want to bring it to a form of t e to the t. Well, we kind of got the e to the t part, right? This is our t. Yep. In order to bring that t over here, we kind of need to do a little bit of manipulation, right? Like what? We have to multiply both sides by negative 1/2 and then this whole thing. Make sense? Okay, let's do that. Let's multiply by negative 1/2 first. Maybe that'll be easier for you, easier to understand. Let's multiply by negative 1/2 and it gives us this. Of course, you have to multiply both sides, so it's going to be on the right-hand side, negative 1/2. Great. Now, we need to multiply by this so that this becomes our t. And that'll be negative z over 2 multiplied by 1/2 ln 2 plus I pi over 2, which is the ln of 1 plus I, remember, times e to the power negative z over 2 multiplied by the same thing, right? I pi over 2, of course, it's not going to fit here. And I'm going to write it as negative 1/2 multiplied by 1/2 ln 2 plus I pi over 2. Awesome. Now we do have t e to the t equals this. So what am I going to do? I'm going to w both sides. And when I do, ta-da-da-da, a miracle happens, right? This becomes t, which is this. Okay? So the left-hand side turns into negative z over t, negative z over 2 multiplied by 1/2 ln 2 plus I times pi over 2. A lot of halves, right? And the right-hand side just becomes, of course, we w both sides. So it's just going to be the w of something like this, negative 1/2 multiplied by 1/2 ln 2 plus I times pi over 2. Maybe we can go ahead and distribute the negative 1/2 so that it kind of looks a little bit better, right? Don't you think? 1/2 ln 2 plus I pi over 2. And on the right-hand side, I'm going to go ahead and distribute to negative 1/2. That's going to give me negative 1/4 ln 2 minus 1/4 I pi. Or you can write it as negative I pi over 4. Okay? Either way is fine. Now, what are we going to do? We need to solve for z, remember? No matter how ugly that is. We're going to go ahead and divide both sides by that. And then we'll do the negative 2. So let's go ahead and do it in two pieces again. I'm going to divide both sides by that first. So it's going to be w of negative 1/4 ln 2 minus I pi over 4 divided by 1/2 ln 2 plus I pi over 2. And then finally, we're going to multiply both sides by -2. So our expression z becomes -2 times w of -1/4 ln 2 minus I pi over 4 all over 1/2 of ln 2 plus I pi over 2. If you're wondering what that's going to look like, because z is going to be a complex number, just like in the form of a plus bi, you can go ahead and use Wolfram alpha and find out the exact answer. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe. Take care. Again, Physic Trapella. Thank you for the idea. Keep them coming. Until next time, bye-bye.